This is video 33 in the series of reinforced concrete slabs, but it will be dealing with columns, and we will work out some examples. Example 1, we have a rectangle or a square column, cross section 300 by 300. It's reinforced with 6 diameter 16. There's a concrete cover of 40, stirrups of 10 millimeters, and a concrete weight of C30-37, and the load on this column is 1000 kilonewton, with a bending moment because of an asymmetric loading of the slabs on top. It's 50 kilonewton meter. The creep coefficient is 2, and all units in this exercise is kilonewton, kilonewton meter, and millimeter. So we'll now check if this column is okay regarding bearing capacity. We just, as a first check, we take the interaction diagram of the cross section, like we have seen in the lessons of concrete beams. And then it gives you the blue curve. That's all the combinations of N and M that will fulfill all conditions. And now we plot our condition, which is 1000 kilonewton and 50 kilonewton bending moment, and we see we are inside the curve. So this is fine, no problem. But we have not checked slenderness now. So this is by neglecting buckling. You see we have a lot of reserve capacity. Now we'll check for first order bending moments. It's of course E0, it's M1000 divided by the N, so E0 is 50 millimeters. But E0 must be greater than H over 30, the size of the column divided by 30, it's 10, must be also greater than 20, and it must be greater than 20. EA, the accidental eccentricity, is the effective length divided by 400, and the is 5.25 millimeters. The first order eccentricity at the top of the column is then the first order at the top is E0, it's 20, plus EA, no, sorry, E0 is 50, plus E0, and that's 25.25, so it's 55.25. And on the bottom, it is also 55.25 millimeters. First order bending moment on the top is then the normal force times the eccentricity is 55 kilonewton meter. And the first order bending moment on the bottom is also 55. So the mean first order bending moment is of course also 55. Now we have to check, is buckling needed? Is the buckling check needed? Well, first we calculate the limit value of the slenderness lambda limit. To do so, we need the load rate, which is the normal force divided by the cross sections and the maximum compressive stress, and N is equals to 65%. A is 0.71, omega the mechanical reinforcement ratio is 0.34. The B value depends on the mechanical reinforcement ratio, and B is 1.3. Rm is of course 1, and C is 1.7 minus 1 is 0.7. Now we can calculate the limited value of the slenderness, which is 16. You see this is a very low value. So it means that in almost all cases you need to take care of the second order bending moment. We will calculate the slenderness of the column. It's the effective length divided by the radius of gyration. And doing so, we achieve E equals to 87 and lambda is 24. So we see lambda should always be smaller than 140, so that is fulfilled, that's okay. But we see that the slenderness of the column is bigger than the limit value of the slenderness, so we have to take second order bending moments into account. So the check for buckling is needed. Second order bending moment, we'll use the method of nominal curvature, and we see that the for n ball equals 2.4, nu is 1 plus omega. It's just filling in some equations, and by doing so we obtain, this is now the R0 and R, and then we can calculate the second order eccentricity, which is 11 millimeters. It is just working out the set formulas, nothing more, nothing less. And the moment of in second order is then the normal force times 11 millimeters. And I divide by 1000 because I work in kilonewton and in millimeter. So M2 is 11 kilonewton meter. It means that the column must be checked for bending and normal force, but the bending moment must be increased by the first order bending moment plus the second order bending moment. And you see the second order bending moment is almost 1/5 of the total of the primary bending moment. So it's not negligible. So now we can check with the column with N and M with combined bending. We take our interaction diagram. That was the starting point. And now you see we went up and we arrive at this point. So now this column is checked with this method and its column is fine. We can also use the method of moment magnification factor. That's the second method, which is much easier and much faster. The critical load is equal to this amount. We replace ECM by EC equals to ECM divided by 1 plus K times V, just to take into account the creep of the column. And then the critical value, load value, is 16,535 kilonewton. We apply the formula of the moment magnification factor with beta m equals to pi squared over 8. And we have a bending moment of 60 kilonewton meter. And you compare that with the previous method, we had 66. So there is a difference, but not that much. That was for the first example. Now we'll take a second example, which is a column of size 20. It's only 2 meters high. So that's not very high, only 2 meters. And we have a simple column of 20 by 20 centimeters. For instance, a column of a carport or something like that. It's reinforced by 4 diameter 16, which is really a lot, in fact. 4 diameter 16, concrete cover 40, stirrup 10, C30 37, a creep factor of 2, and it's loaded by 500 kilonewton, which is not much. There's no bending moment on it. And let's suppose that this is just centric placed on the column, and there is no bending moment, no external bending moment. We do the calculation, and we find that because the dotted red line is the minimum eccentricity that you have to take into account. Remember, column is always calculated with combined bending, so you always have a bending moment, and this is the minimum value. That's why there is a dotted red line. And you see that according to this first impression, the column is fine. 2 meter high, 20 to 20 centimeters in cross section, loaded with 500 kilonewton, it's fine. The first order bending moment is given by E0, which is m over n, and that means 20 millimeters. But E0 must be greater than h over 30, which is 7 millimeters or 20. So, and the accidental eccentricity is the effective length divided by 400, or it's 10 millimeters. And the first order eccentricity on top is then E0 plus EA, gives you 30 millimeters. On bottom, it's the same. The first order bending moment on top of the column is then the normal force multiplied by the eccentricity. It's 15 kilonewton meter. And the first order bending moment at the bottom is also 15 kilonewton meter. And of course, the mean first order bending moment is 15 kilonewton meter. Now we will see if buckling is needed. For that, we will calculate the limit value of the slenderness lambda limit. First, we calculate the load rate, which is the total normal force divided by the cross-section and divided by the maximum compressive concrete stress. And the load rate is high, it's 74%. Factor A, depending on the creep factor, is 0.71, which is a normal value. And the mechanical reinforcement ratio is 0.51. Then the factor B, depending on that mechanical reinforcement ratio, is 1.42. And Rm is of course 1 because MO1 and MO2 are equal. And the coefficient C is then 0.7. The limit value of the slenderness is then 16.6. We calculate the slenderness of the column, which is L0, the effective length, divided by the radius of gyration. When we do that, we have 69 as slenderness. Must be smaller than 140, that is okay. Then 69 must be smaller than 16 for not having buckling taken into account, but this is not the case. So we need to check for buckling, and we see already that the buckling will be dominant in this case. The second order bending moment, we use the formulas like we have developed them in the previous slides. It's just filling in the different values. And we use, of course, sorry, I didn't mention that, the method of nominal curvature first. And we see that we have then we are able to calculate the eccentricity of the second order, which is 41 millimeters. And the bending moment in the second order is now 21 kilonewton meter. It's nothing difficult about this method. It's just filling in painfully all the different formulas. So the column must be checked with a bending moment equal to the first order bending moment, which was 0, and the second order bending moment, which is now 35 in total. When I say the first order bending moment was 0, it was in the sense of there was no external force causing the bending moment, but you always have to put a minimum eccentricity to the normal force. So this bending moment was 10 plus the bending moment coming from the second order displacement. You see, this is substantial. It's 36 kilonewton meter, even though your initial bending moment was 0. And the normal force is not high, it's 500. Now we will plot NM in our combined bending graph that will come. We will just have as a verification, use the method of the moment magnification factor, and we calculate the critical buckling force, and we use this formula for the moment magnification factor, and we find 38 kilonewton meter, which is similar to what we found just before. And then we can plot them in the interaction diagram in ULS persistent, and you see this was the initial value, and now we are far outside this curve. So the column is buckling out. Now, what we can do is we can say, okay, the column is now from 500 kilonewton normal force, centrically placed, it's buckling out. There are 4 diameters 16 as reinforcement in a section of 200 by 200 millimeters. So that's heavily reinforced. Now we lower the normal force from 500 to 400, and still it's not enough. Only when we arrive at 300 kilonewton, then the column will be all right, but just barely right. So you see that instead of 500 kilonewton, which is this point here, we can only load the column with 300 kilonewton, and afterwards it will buckle. Now, what can we do when we increase? We are here at this point, and we increase no, we were here from the point. Now we will increase the reinforcement, and we say we reinforce against buckling. No, this is not a very wise decision because it does not help you a lot. It helps you when you are just on the limit, somewhere on the limit, then you can make it a little bit better by increasing your reinforcement. But in general, when buckling is dominant, it's not very wise to cope with that by using more reinforcement. What can you do is you can change the column dimensions. And for instance, we were now here with a column of 200 by 200. If you increase the column in size in 240 by 240 with the same reinforcement, then you have a large margin. Then it's okay. Then the column is fine. So designing against buckling should be done by increasing the dimensions of the column.